Welcome you all to this first lecture on the topic sequence and series. To begin with, let me draw your attention to the fact that the two words, namely sequence and series, are used interchangeably in day-to-day life. We don't make any distinction between the words sequence and series in day-to-day life. For instance, when we say a sequence of events, or when we say a series of mathematics tests, or when we say cricket test match series. In these instances, a sequence or a series is used to suggest succession of events. Or succession of objects. By succession, I mean a ordered list. To sum up, we don't want to make any distinction between the two words sequence and series in day-to-day life. However, in mathematics, the two words sequence and series are used with separate technical meaning. Having said this, a natural question at this juncture is, what are the different technical meaning that we want to attach with the words sequence and the series? Or how do they differ? Further, is there any relationship between these two words? And these questions will be answered as the course progresses. Let us look at the word sequence in mathematics. To begin with, let me give a couple of examples. First example, I list even integers. As you all know, even integers, to be specific, even positive integers can be listed as 2, 4, 6, 8, and so on. The nth even integer will be 2n, so on and so forth. As another example, let us consider the process of dividing ten by, let us say, 3. Let us list the successive quotient obtained when we divide ten by 3 at different steps. So, what we want to list is the quotient that we obtain in the division process while we perform the division in step by step process. So, let us divide 10 by 3. So, 3, continuing 3.3, 3.33 and so on. This is what I mean by listing successive quotient when we perform the division 10 by 3 stepwise. As another example, let us consider the so-called rabbit problem. Assume that a pair of rabbits, say one male and one female, is put in a field. Assume that after 1 month the rabbits get sexually matured and the female produces a new pair of rabbits. Again, pair consists of male and female at the end of 2nd month. Let us consider some idealistic circumstance. Let us say that the rabbits never die, and let us say that each female rabbit produces a new pair of rabbits, again male and female, in every month from 2nd month onwards. Is it clear? So, this is the situation. And the question is, how many pairs of rabbits are there at the end of 1 year, let us say. This is the question. The solution, generation by generation, produces a list of numbers, the so-called, historically called Fibonacci numbers. Let us have a try and list some Fibonacci numbers. Let us try to find how many pairs of rabbits are there at the end of 1 month, 2 months, 3 months and so on. Let us eventually find out how many pairs of rabbits are there at the end of 1 year. We started with 1 pair of rabbit, 1 male and 1 female. Recall that at the end of 1 month, the rabbits get matured, but then it does not produce any new rabbit. So, at the end of 1 month, total pair of rabbits in the field is again 1. At the end of 2nd month, the female rabbit produces a new pair of rabbit, so that totally there will be 2 pairs of rabbit at the end of second month. Now recall that a female produces a pair of rabbit every month from second month onwards. So at the end of third month, there will be 3 pairs of rabbit. One pair newly produced by the original female that we put in the field. Now, at the end of 4 months, the female rabbit created at the end of second month will produce a new pair, and hence there will be total of 5 pair rabbit at the end of 4 months. You can continue this and try to list what will be the number of pairs of rabbit at the end of 5th month, 6th month, and so on, keeping in mind that the female rabbit produced 2 months ago will produce a new pair of rabbit. This problem was originally posed by Fibonacci, and the numbers created, which stands for the number of pairs at the end of 1 month, 2 months, and so on, is called Fibonacci numbers. Let us continue with another example. Now, the problem is related to a depositor and a bank. Assume that a bank pays interest at the rate of 10% per annum. Further, assume that a depositor invests ₹1, let us say, at the bank. If the bank calculates simple interest, then the question of what will be the amount the depositor get after 1 year can be obtained from the formula that you have studied earlier, amount equal to principal plus interest. Recall the investment principal is ₹1. In case of simple interest, the formula is PNR, where P stands for the principal, N stands for the number of years, and R stands for rate of interest per annum. In this case, it is easy to calculate that the interest amounts to 1 into 1 into 1 by 10, namely 1 by 10, and hence the amount at the end of 1 year will be 1 plus 1 by 10. Now, let us assume that the interest is computed as compound interest. Let us further assume that the interest is compounded twice a year. In that case, it will yield an amount equal to 1 plus the interest for half year, namely 1 into 1 by 2 into 1 by 10 is equal to 1 plus 1 by 20 at the end of half year, first half year. This will be the amount for the second half. For this amount, the interest will be the amount into number of years, it is half, into rate, and hence the interest for the amount yielded in first half will be this, and total amount at the end of 1 year would be 1 plus 1 by 20, which is the amount after first half year, plus 1 by 20 into 1 plus 1 by 20, which amounts to 1 plus 1 by 20 the whole square. Do you see it? Now, let us assume that the bank calculate compound interest and compounded thrice a year. By a similar procedure, you can see that the amount at the end of 1 year, when interest is calculated, in a compounded fashion thrice a year, at equal rest, of course, will be 1 plus 1 by 30 the whole cube. It is not hard to calculate. Please have a try. Suppose we assume that the bank calculates interest compound fashion, but compounded n times in a year at equal rest, let us say. Amount after 1 year would be equal to 1 plus 1 by 10n the whole power n. Now, if we list the amount we obtain if the bank calculates simple interest will be 1 plus 1 by 10. Amount obtained if the bank compounds interest half yearly will be 1 plus 1 by 20 the whole square. The amount that depositor gets if the bank calculates compound interest compounded thrice a year will be 1 plus 1 by 30 the whole cube, etc. If we assume bank compounds interest n times an year at equal rest, then the amount obtained will be one plus 1 by 10n the whole power n. We can continue listing many examples, but what I want you to observe through this example is that what we deal with in the first example, namely list of even integers. In the second example, namely the list of successive quotient obtained when 10 is divided by 3 step by step manner. And in the rabbit problem, which gives number of pairs of rabbits at the end of n month and so on, we deal with ordered list of numbers. Do you see it? In all these examples, in one way or the other, we deal with ordered list of numbers. A sequence informally is an ordered list of numbers. For instance, let us have 1, 3, 5, 7, 9, etc. Let us have 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, etc. Slightly more generally, let us have the list A1, A2, A3, etc., AN, etc., where AIs are numbers. This is what informally a sequence is. By this time, whenever you hear a word sequence, you should attach it with an ordered list of numbers. When I say ordered, it should be borne in mind that the first member in the list of A1, A2, A3, so on, AN is A1. Second number in the list is A2. Third number in the list is A3 and so on. Thus, though it may not be apparently visible, there is a input-output arrangement with the place taking the role of input. That is, first place, second place, third place, and so on takes the roles of input, and the numbers we list A1, A2, A3, and so on take the role of output. In other words, when we list A1, A2, A3, and so on, and we emphasize that order is important, what we mean is first place number A1 occurs, second place number A2 occurs, third place number A3 occurs, and so on. Could you see an input-output arrangement here with inputs as the places 1, 2, 3, and so on, and output as the numbers we listed A1, A2, A3, so on? Yes. Recall that an input-output arrangement that is a rule which gives a unique output to each input, is what we call mathematically as function. So, associated with a sequence, in fact, there exists a function. And what is the domain of this function? The places which number occur in which place takes the role of the domain. So, 1, 2, 3, etc. constitute the domain, and the numbers we list take the role of range. Hence, a sequence can be more formally defined as follows. A real sequence is a function f from set of natural numbers to the set of reals. If we designate set of natural number by n and set of reals by r, a sequence is a function f from n to r. More precisely, a real sequence is a function from n to r. F of n is what we write as a n. When we list a1, a2, a3 and so on, inherent with it there is a function which sends 1 to a1, 2 to a2, 3 to a3 and so on. If that inherent function is named as f, f of 1 is a1, f of 2 is a2 and so on. The number an we list in nth place of a sequence is actually the function evaluated at n. To sum up, sequence informally means an ordered list of numbers and more formally it is a function f from set of natural numbers to r. For instance, in the example of list of even natural numbers 2, 4, 6, 8, the nth even natural number is 2n and so on, the associated function f can be written as f from n to r, f of n is equal to 2n. When you hear the word sequence, you should immediately attach it with a function with the domain as set of natural numbers. In fact, the codomain can be different from R. It can be a general set, yes, but we will confine to the case of real sequence in the sense that the elements that we list are always real numbers. Having said this, let me set some notation. A sequence AN can be represented or described by writing the rule that provides nth term, a general term of the sequence. By the way, when we have a sequence A1, A2, A3, etc., AN, etc., A1, A2, etc., those numbers are called terms. One way to describe a sequence is write AN in terms of n. For instance, the sequence of even integers, positive even integers, can be described by writing AN is equal to 2n, n is equal to 1, 2, 3, etc. This is one way of describing a sequence. Another way to describe a sequence is to list its terms. And write a sequence as A1, A2, so on, AN, and so on. In a compact manner, this can be written also as set AN, n is equal to 1 to infinity. So far, we have seen two ways of describing a sequence. One, write a rule that provides you the nth term in terms of n, or we can list the terms inside a set, set A1, A2, A3, and so on, AN, and so on, or in a compact manner it can be written as set AN, n equal to 1 to infinity. If you recall the examples we started with, more specifically in the rabbit problem, you can see that we have listed some few terms of the sequence. At the end of 1 month, the total pair of rabbits available in the field is 1. At the end of 2 months, total pair of rabbits available in the field is again 1, and then 2, 3, and so on. You can observe that at a given stage, say at the end of n month, the number of rabbits will be the number of pairs of rabbits available at the end of previous month plus number of pairs of rabbits available 2 months before, because each rabbit 2 months old can produce a new pair. you can observe that a n is equal to a n minus 1 plus a n minus 2 for every n greater than or equal to 2, and instead of writing or describing the number of pairs of rabbit in the end of n months in terms of n, most easiest way as far as this problem is concerned is to write the nth term in terms of previous terms. Such an expression which describes a sequence by writing a particular term using previous terms is called recurrence relation. Thus, recurrence relation is another way to describe a sequence. To sum up, a sequence can either be described with the help of a function which provides the nth term in terms of n. It can be listed like this inside the set notation, or in some specific problems it will be easier to describe a particular term in terms of the previous terms, and that is called recurrence relation. At this juncture, I should make a remark concerning the notation of a sequence using set. As I told previously, a sequence can be described inside a set like A1, A2, A3 and so on An. But it should be borne in mind that a sequence is different from set. For instance, whereas in set, the order in which the elements occur is not important, whereas in sequence, the order in which the elements occurs it matters. In other words, sequence 2, 4, 6, 8, etc. is different from sequence 4 to, let us say, 8, 6, etc. for instance, whereas as a set both are same. Another reason that I can give why sequence should be treated different from set is the following. Consider the sequence n is equal to 1 to infinity, written in more expanded form as, let us say, 1, 1 by 2, 1, 1 by 3, 1, 1 by 4, so on and so forth. More precisely, it can be described as follows: a 2n minus 1, that is odd terms, first term, third term, fifth term and so on, is 1, for every n element of n, and even terms, second term, so on, is of the form 1 by n. The second term A2 is 1 by 2, the fourth term A4 is 1 by 3, and sixth term A6 is 1 by 4, and so on. That is, the second term 2 into 1 is 1 by 2, the fourth term A 2 into 2 is 1 by 3, the sixth term A 2 into 3 is 1 by 4, and so on. So, A2n, if you see the pattern, it will be 1 by n plus 1. You can cross check it. So, this is the sequence inherent with the list 1, 1 by 2, 1, 1 by 3, 1, 1 by 4, and so on. The odd terms are 1, and the even terms A2n can be described with the help of 1 by n plus 1 for every n in n. Whereas, underlying set here, set an, recalling that in the set we do not write the elements repeated, just 1, 1 by 2, 1 by 3, 1 by 4, and so on. So, in a sequence, the element can be repeated, and in the set we do not write the same element repeatedly several times. Thus, though we use the notation set an n equal to 1 to infinity for a sequence, keep in mind that sequence is different from a set, mainly in the sense that sequence is an ordered list, whereas in a set we do not bother about order in which elements occur. First, by recalling that in the precise definition of a sequence is defined as a function with the domain as set of natural numbers, that is, a sequence is a function f from n to r. Recall this fact. Now, consider the list, for instance, 12, 14, 16, 18, and so on. Can you recognize the pattern? It is not hard to recognize the pattern and write an. If it follows this pattern, the nth term will be 10 plus 2n. Am I right? The first term is 10 plus 2. The second term is 10 plus 2 into 2. The third term is 10 plus 2 into 3, that is 16, and so on. So, the sequence 12, 14, 16, 18, etc. can be described as sequence an, n is equal to 1 to infinity, where an is expressed with the help of the rule. I would like to draw your attention to the fact that the same sequence can also be expressed as Bn, where n is equal to 6 to infinity, Bn is equal to 2n. B6 is 2 into 6, 12. B7 is 2 into 7, 14, and so on. So, the same sequence can be described with Bn, where Bn is given by the rule 2n, but now n starts from 6 and continues up to infinity. So, this remark is to pronounce that though in the definition of a sequence we took function from n to r, sometimes it is convenient to work with a subset of n starting from say n naught. Instead of whole n, we may work with the set n naught plus 1 and so on. In the previous example, we started with B6, B7 and so on. This remark should shed light on the fact that a sequence can be defined as a function from some subset of natural numbers to R, though it is customary to define it from set of natural numbers. Recall the notion of term of a sequence. If you have the sequence A1, A2, A3 and so on, the elements AIs are called terms. There may be circumstances where we want to have sequence with finite number of terms. In the previous list of examples that we have seen for rabbit problem, we were asked only to find how many pairs of rabbits are there at the end of 1 year. So, our list will be finite. We have to deal only up to number of pairs of rabbits at the end of 12 months. Like this, there are instances where we would like to have sequences with finite number of terms, and such sequence with only finite number of terms are called finite sequence. A sequence such as the list of all even integers consists of infinite number of terms, and sequences with infinite number of terms are called infinite sequences. We will be mainly concerned with infinite sequences, that is a sequence having infinite number of terms. Going back to the formal definition, since we have to incorporate also sequences with finite number of terms, a sequence may be defined as a function from set of natural numbers to R, or a finite subset of set of natural number 1, 2, 3 etc. up to k to R. Let me write it here. A sequence, in fact a real sequence, is defined as a function from set of natural numbers denoted by n to R, or a function from a subset 1, 2, 3 etc. up to k of n to R. In the definition, we added a function from a subset 1, 2, 3 etc. up to k of n to R just to incorporate finite sequences. At the end of this lecture, you should be able to understand informal definition of sequence, namely a sequence is an ordered list of real numbers. Formal definition, a sequence is a function from set of natural numbers to R or a subset of natural numbers to R. Various ways of describing sequence. One is using the notation an, n is equal to 1 to infinity, and listing it as a1, a2 etc., or writing an in terms of n using a rule or with the help of recursive definition. You should also know why a sequence is different from sets. We shall proceed with more examples of a sequence and other notions regarding sequence in next few lectures. Thank you.